Now let's look at some innovative vapor compression refrigeration systems. The simple vapor compression refrigeration cycle is the most widely used one, and it is adequate for most applications. The ordinary vapor compression systems are simple, inexpensive, reliable, and practically maintenance free. However, for large industrial applications, efficiency, not simplicity, is the major concern. Also, for some applications, the simple vapor compression refrigeration cycle is inadequate and needs to be modified. So we will look into some of these modified refrigeration systems. Let's look at the cascade refrigeration system now. Some industrial applications require moderately low temperatures, and the temperature range they involve may be too large for a single vapor compression refrigeration cycle to be practical. A large temperature range also means a large pressure range in the cycle and a poor performance for a reciprocating compressor. One way of dealing with such situations is to perform the refrigeration process in stages, that is, to have two or more refrigeration cycles that operate in series. Such refrigeration cycles are called cascade refrigeration cycles. A two-stage cascade refrigeration cycle is shown in this figure. The two cycles are connected through the heat exchanger in the middle, which serves as the evaporator for the topping cycle, which is cycle A, and the condenser for the bottoming cycle, which is cycle B. Assuming the heat exchanger is well insulated and the kinetic and potential energies are negligible, the heat transfer from the fluid in the bottoming cycle would be equal to the heat transfer of the fluid in the topping cycle. So the ratio of mass flow rates through each cycle, you can see the mass flow rate of cycle A, m dot sub A divided by m dot sub B would be equal to H2 minus H3 divided by H5 minus H8. Also, the coefficient of performance of the cascade refrigeration cycle would be given by the equation that is given in the slide above. In the cascade system shown in the figure, the refrigerants in both cycles are assumed to be the same. This is not necessary, however, since there is no mixing taking place in the heat exchanger. Therefore, refrigerants with more desirable characteristics can be used in each cycle. In this case, there would be a separate saturation dome for each fluid, and the TS diagram for each cycle would be different. Also, in actual cascade refrigeration systems, the two cycles would overlap somewhat, since a temperature difference between the two fluids is needed for any heat transfer to take place. It is evident from the TS diagram that the compressor work decreases and the amount of heat absorbed from the refrigerated space increases as a result of cascading. Therefore, cascading improves the coefficient of performance of a refrigeration system. Some systems use 3 or 4 stages of cascading. Now let's look at multi-stage compression refrigeration systems. When the fluid used throughout the cascade refrigeration system is the same, the heat exchanger between the stages can be replaced by a mixing chamber, which is called as a flash chamber, since it has better heat transfer characteristics. Such systems are called multi-stage compression refrigeration systems. A two-stage compression system is given in this figure. In this system, The liquid refrigerant expands in the first expansion valve to the flash chamber pressure, which is the same as the compressor interstate pressure. Part of the liquid vaporizes during this process. The saturated vapor, which is of course given in state 3, is mixed with the superheated vapor from the low pressure compressor, which is state 2, and the mixture enters the high pressure compressor at state 9. This is in essence a regeneration process. The saturated liquid in state 7 expands through the second expansion valve into the evaporator, where it picks up heat from the refrigerated space. The compression process in this system resembles a two-stage compression with intercooling, and the compressor work decreases. Care should be exercised in the interpretations of the areas on the TS diagram in this case, because the mass flow rates are different in different parts of the cycle. Let's look at multi-purpose refrigeration systems with a single compressor now. Some applications require refrigeration at more than one temperature. This could be accomplished by using a separate throttling valve and a separate compressor for each evaporator operating at different temperatures. Such a system, however, is bulky and probably uneconomical. A more practical and economical approach would be to route all the exit streams from the evaporators to a single compressor and let it handle the compression process for the entire system. Consider, for example, an ordinary refrigerator freezer unit. A simplified schematic of the unit and the TS diagram of the cycle are shown here. Most refrigerated goods have a high water content, and the refrigerator space must be maintained above the ice point to prevent freezing. The freezer compartment, however, is maintained at about -18 degrees C. Therefore, the refrigerant should enter the freezer at about -25 degrees C to have heat transfer at a reasonable rate in the freezer. If a single expansion valve and the evaporator were used, the refrigerant should have to circulate in both compartments at about -25 degrees C, which would cause ice formation in the neighborhood of the evaporator coils and dehydration of the produce. This problem can be eliminated by throttling the refrigerant to a higher pressure, hence a high temperature, for use in the refrigerated space, and then throttling it to the minimum pressure for use in the freezer. The entire refrigerant leaving the freezer compartment is subsequently compressed by a single compressor to the condenser pressure. Now let's look at refrigeration systems that are associated with liquefaction of gases. The liquefaction of gases has always been an important area of refrigeration, since many important scientific and engineering processes at cryogenic temperatures, that is temperatures below about -100 degrees C, depend on liquefied gases. Some examples of such processes are the separation of oxygen and nitrogen from air, preparation of liquid propellants for rockets, the study of material properties at low temperatures, and the study of some exciting phenomena such as superconductivity. At temperatures above the critical point value, a substance exists in the gas phase only. The critical temperatures of helium, hydrogen, and nitrogen, three commonly used liquefied gases, are -268 and -240 and -147 degrees C respectively. Therefore, none of these substances exist in liquid form at atmospheric conditions. Furthermore, low temperatures of this magnitude cannot be obtained by ordinary refrigeration techniques. Then the question that needs to be answered in the liquefaction of gases is this: how can we lower the temperature of a gas below its critical point value? Several cycles, some complex and some others simple, are used successfully for the liquefaction of gases. We will discuss the Lindy-Hampson cycle, which is shown schematically in the TS diagram in this figure. Makeup gas is mixed with the non-condensed portion of the gas from the previous cycle. The mixture at state 2 is compressed by a multi-stage compressor to state 3. The compression process approaches an isothermal process due to intercooling. The high pressure gas is cooled in and in an aftercooler by cooling the medium or by a separate external refrigeration system at state 4. The gas is further cooled in a regenerative counterflow heat exchanger by the uncondensed portion of gas from a previous cycle to state 5, and it is throttled to state 6, which is a saturated liquid vapor mixture state. The liquid at state 7 is collected and the desired product, and the vapor at state 8 is routed through the generator to cool the high pressure gas approaching the throttling valve. Finally, the gas is mixed with fresh makeup gas and the cycle is repeated.